Okay, good afternoon, ladies and gentlemen. It's May 2, 2024, and the time is 4:02 p.m. It's May 2. Okay, my topic for decision will be a random topic, and this falls under the study of differential calculus. So, for this afternoon, I will be discussing the so-called many of you guys are bored with differential calculus, but what I will be discussing this afternoon will be the importance of differential calculus in real life. This is an actual problem because without knowing our knowledge of differential calculus, we cannot solve this problem. It could be solved, but it will be a trial and error method. But if we try to use differential calculus, rest assured that we will be getting the correct dimensions for the required problem. Okay, let's proceed. This is a random topic and it falls under the study of differential calculus. Okay, I will try to read the problem. A closed cylindrical can is to have a volume of 108 cubic inches and a minimum total surface. We have a cylindrical can. This is plastic, but the problem says it's cylindrical can. So we assume for the meantime that this is a cylindrical can. This is a cylinder. So it should have a radius here and it should have a height. The volume of the can is 108 cu inch, or this is red cubic inches. Okay, 108 cubic inches. So the volume of the cylindrical can is 108 cubic inches. And a minimum total surface. Total surface meaning the surface at the top portion, surface at the bottom, and the curved side. The condition is that if we try to manufacture this cylindrical can, the total surface should be minimum. Why minimum? Of course, in the manufacturing process, if we could minimize our material, of course, we will maximize our profit. Okay, so this is where the importance of differential calculus now. Without knowing differential calculus, we could not compute for the required radius in altitude to give us the minimum total surface. Okay, the problem is asking find the base radius and the altitude. The problem is asking what will be the base radius in altitude. This is the total diameter, right? So the total length of this one will be twice the radius, right? Because at the center here, that will be the radius, right? So this total base area length here should be twice the radius. And this is actually equal to the diameter. And the unknown altitude of the can is actually represented by h. So this is h and this is 2r. So for the meantime, let's assume that this is a cylindrical can. This total length here is twice r, and this side here is h. And the given volume. Of course, if we are to manufacture a cylindrical can, we put something inside. So actually we know the volume, and the volume is actually 108 cubic inches. In engineering, we write cubic inches as simply inch raised to the third power. And this is red cubic inches, 108 cubic inches. So the problem is what will be h equal to and what will be r equal to. Okay? So when we try to compute for the volume, it will give us 108 cubic inches. And the surface area of the tin can that will be needed in the manufacturing of the can will be minimum. Of course, the management would like that the material thing should be minimum. Okay, so if the material thing should be minimum, the profit will be maximum. Okay, this figure, I will discuss this one after bringing out the solution. So the figure for this one, like what I said, this will be cylindrical can. This is not the can, it's plastic. It is this, right? So this is twice R, this is H. Okay, let's try to bring out the solution of this one, but we must have to bring out a representation. Small letter H will be the altitude, small letter R will be the radius, capital letter S will be the total surface. Total surface meaning the area of the top portion plus the area of the bottom portion plus the area of the curved surface around. Okay, and what is given in the problem? The volume is 108 cubic inches. This is fixed. Okay. Actually, if we are given the volume, we could take any radius in height to satisfy this volume, but we do not know if that radius in altitude will give us the minimum total surface. So, to determine the correct value of R and H, we must have to use differential calculus. So, the concept here is, this is now the importance of differential calculus, right? So the title of the topic for this afternoon is actually the importance of differential calculus in manufacturing. Okay, what is the condition? The condition of the problem is capital letter S should be minimum. Management would like that the total materials needed in the manufacture of the cylindrical can should be minimum. So if we could minimize our material thing, of course, our profit will be maximum. Okay, let's bring out the solution. And here, before I will bring out the solution, I want to emphasize that small letter h, radius, and s are all variable. These three here are all variable. Because to satisfy the volume 108, we could take any value of h, we could compute for the corresponding value of r, but we are not sure if the total surface will be minimum. So for us to be sure that the correct height and altitude will give us the minimum total surface, we will be using differential calculus. Or how do we proceed with the solution? We needed formulas. The volume for a cylindrical can is represented by this one. We needed this formula. And what's the other formula that is needed? Capital letter S. Capital letter S is actually the total surface area in the manufacture of the cylindrical can. It will be the area of the top plus the area of the bottom plus the curved surface. The area of the top will be, of the bottom and top are actually the same, pi r square, right? They are circle. It is top and bottom, so this is multiplied by 2. Plus, the area of the curved surface will be the circumference. If we try to draw the circumference is actually 2 pi r. This is the area of the curved surface and this is h. So the curved surface around the cylindrical can will be this. And if we try to compute for the area, it will be h times the circumference that goes around. And it is actually represented by 2 pi r. So this should be 2 pi r times h. So we will be using this first formula on the volume, and we will be using the formula on the total surface, in which we derive, that is 2 pi r square plus 2 pi r s. Okay? We are studying engineering, we are on differential calculus, we needed formulas, because without formulas, okay, we could not proceed with the solution. Okay, let's proceed with the solution now. Volume is equal to pi r square s, right? We are given the volume of the cylindrical can. The contents of this one, if we try to manufacture this one, should be 108 cubic inches. So this is 108 pi times r square times h. For the meantime, we do not know the value of r. For the meantime, we do not know the value of h. So it seems we are given equation number 1 now involving r and h. Okay? It's just simply a function of r and h, and they should be equal to a certain constant. We call that equation number 1. That's why 108 equal to pi r square h. There are two variables involved. We call it equation number 1. Right? We are now deriving the formula on how to bring out the total surface. Let's get back to the formula and taking the total surface. Total surface is actually 2 times pi r square plus 2 pi r multiplied by h. This is equation number 2. For this equation number 2, there are actually 3 variables, right? It's s, r, and h. But we are given the relation of h in terms of r by using equation number 1. So rewriting equation number 2, s now will be 2 pi r square plus 2 pi r. And we shall try to replace this one by this value here. We will compute for h here. H here will be 108 over pi r square. So this is 108 over pi r square. Simplifying this one, this is S now, capital letter S. The total surface area required should be equal to 2 pi r square. This is now cancellation, guys, where many of you made some mistakes. The operation on the numerator are multiplication, right? This is multiplication. 2 pi r times 108 over pi r square. So actually, this pi here cancel with this pi, right? And this r here cancel with this. What remains is 1 r at the bottom. And 2 times 108 will be 216. So after the cancellation, s now will be 2 pi r square plus 216 over r. So it seems we are now given an equation involving s as a function of r. It seems this is y and this is a function of x. We are fond of the variables y and x, but for the meantime, just interchange y for s and x for r. So it seems we are now given s as a function of r, right? Forget the x and y. But they are the same. We just change the designation. Okay? If we try to graph of this one, it should be a parabola opening upwards. So we'll go back to the first figure here. It should be a parabola opening upwards. So there should be a minimum point for the graph of this one. The minimum point is actually at this one here, at this point here. Because if we try to take this is s as a function of r, right? That's what we derive. So it seems this is y and this is x. We just replace x by r and s by y. So forget y and x for the meantime. This is s, is r. This equation here is actually a parabola that opens upward, and there should be a minimum point, right? And what is that minimum point? At this minimum point, there is a value r and s. Okay? And we are sure that if we try to take the first derivative of s with respect to r and we equate it to 0, we are sure that it is really a minimum point. Okay? That's why minimum here. Right? We are sure that what we will be getting, the value of r and h, will give us the minimum total surface. The graph, this one is this one. So if we now try to use our knowledge of differential calculus, we take the s is variable, r is variable, we take the derivative of ds over dr. Ds over dr should be equal to the right hand side, 2 pi is constant times r square, it should be 2 pi. R square falls under the power formula. 2r times 1. Right? Decrease in power by 1. Plus, this is a constant over a function. there is a direct formula on how to compute for the derivative of this one. It will be that constant preceded by negative sign all over the square of the function. Or if you don't want to use that formula, you can use the quotient formula. What will come out is just the same as this one. Then for minimum total surface, we will set ds over dr equal to 0 for minimum total surface. Okay? This is the graph opening upwards. This is the minimum point. We set ds over dr equal to 0. We could compute for the required value of r, which will give us the minimum total surface. So equating the left hand side to 0, may still ang dollar? 0 equal to 4 pi r. This is plus and minus, this is minus 216 over r squared, right? Then we will transpose this to the left. It will become plus 216 over r squared equal to 4 pi r. 4 pi r, actually, this is actually all over 1. Then we try to cross multiply. Right? 4 pi r times r will be 4 pi r cubed equal to 216 times 1 is just 216. This is with the 4 pi. Right? But we divide both sides by 4 pi, so this will just be simply r cubed now equal to 216 over 4 pi. And if we try to use our calculator, 216 over 4 pi is 17.198. Okay, that's r cubed. So to compute for r without the power 3, we remove this 3 here, then we raise this to the 1/3. Right? So I place it here, r is actually 17.188 raised to the 1/3. And r is actually 58 inches. Okay? And going back to equation number 1, we know r, so we could compute for h. H now will be 108. We are following equation number 1 over pi times 2.58 squared. If we try to compute the required altitude of the cylindrical can, will be 5.16 inches. So the required radius in altitude is actually, radius is 2.58, volume h is 5.16 inches. So this is 5.16 inches, and the value of the radius is 2.58 inches. Radius. Meaning to say, this radius here is twice to give us the correct height. So if we try to compute for the volume with this given h and r, what will give us will be the volume 108 cubic inches, to be sure. Okay, that's it, guys. That's the importance of differential calculus in real life. We use this in the manufacturing process. Okay? If the problem involves minimization of material things. Okay? That's the importance of differential calculus. Okay. Good afternoon from Los Angeles. This is Professor David Chetalsre.